Okay, so this is actually 5.1. Let's get started. Now, what we're going to be doing, I told you it was going to get a little easier, right? After simplex method. So this class is kind of split up into two parts. You got your matrices, and then you've got your probability. Okay, we're kind of entering the probability part. We're not really going to do probability in this class. Like in this, I mean, this chapter, we are going to do probability in this class. But this chapter can be used in probability. It can be used in thinking. It can be used in counting. What we're going to be talking about today is graph theory. Now, graphs, they're a way to organize information. Okay. Now, I know what you're thinking about graphs. You're thinking about lines. You're thinking about quadratics. You're thinking about all that. We're not doing any of that. Okay. These are no kind of graph you've ever seen before. In fact, quadratics, lines, those aren't really even actual graphs. They're models, right? They're like visual representations of a function. We're not going to be looking at functions at all. We're going to be breaking a graph down to its bare points and talking about what an actual graph is, okay? So most of the time when we're talking about graphs and algebra, we're not really talking about the lines. We're talking about what's behind the lines. You know what I mean? This is a graph with nothing on it. It's still a graph, right? So let's talk about a graph in general. In this unit, we're going to start to learn the ins and outs of graphs and the theories behind them. To start, we're going to need some definitions, and there will be a lot of definitions. You can see I put definition spots on those packets for you. It might be kind of hard to see the definitions, but just do your best you can with those, okay? Ultimately, I'm not going to like put any definitions or anything on the test. You really just need to know what the words mean. You know what I'm saying? But you'll be hearing me say it enough to where you'll probably know what they mean by the end of this. If you don't know the vocabulary in this chapter, you will be screwed. Because the test is going to be stuff like, oh, draw an Euler circuit. You know what I mean? If you don't know what an Euler circuit is, you can't draw one, which means you will get that question completely wrong. On that same vein, it's kind of hard to give partial credit on this test as well. So you want to make sure you know what all this means. Thank you, Tom. Now we're going to start with the main ones. First, a graph. A graph is a finite, there's the class name, collection of points called vertices. So vertices are points on the graph, okay? And these vertices are connected by line segments, and these don't have to be straight. They're straight or curved. So that's not the same definition of line segment from geometry. It's slightly different, okay? And these line segments are called edges. Sometimes a vertex can connect to itself. And the edge that makes this type of connection is called a loop. So vertices are points. Edges are lines that connect points. And an edge that connects a point back to itself in one go without crossing any other points. So it would look like this. Oh, you know what? I got to do it on this. So vertex looks like this. Here's two vertices. Here's an edge. Here's another edge. Okay? Now this edge right here is what I'm talking about when I say a loop. So it looks like this would be a loop, right? But this is not a loop because it's not connecting a vertex back to itself in one edge, right? A loop is one edge. So this is a loop. This is not a loop. That's just two edges, okay? This is going to be the most important word on this slide. The degree. The degree of a vertex is the number of edges that vertex is connected to. Okay? A loop counts as two degrees. So this vertex has a degree of 2. Let's use a different color. This vertex has a degree of 4. So the number of lines sticking out of the point is its degree. You're going to hear me say a lot of times even and odd degrees too. That's just like an odd number of lines sticking out or an even number of lines sticking out, right? So both of these degrees are even because 2 and 4 are even numbers, right? But if I had another edge, something like this, now this degree would be 3, this degree would be 1. So these would be odd degrees, while this one's still even, okay? So the degrees are the number of edges sticking out. Loops count as 2 because 1 going in, 1 going out. Any questions? A little more abstract than what we've been working with, right? But also a little easier to think about, right? All right. Let's continue. Why is a graph? We use graphs to represent real-world concepts to make them easier to look at or understand. Imagine you have a map of the USA, right? But you don't really care about all the blank land. You only care about the major highways and the cities that connect them, the major cities that connect them. Everything else is just, I don't care about that. Well, then you can break down the roads as a graph, right? Within the United States. And then let's say like you got 2 cities really close together or a lot of major highways really close together between like, I don't know, Boston and New York. So those are pretty close, right? Well, you don't have to make them real world distance. You can like move it around. You know what I mean? You can evenly space all the vertices out if you want to and just connect the dots that have major highways connecting them. You know what I'm saying? So a graph makes something so it's easier to look at, makes something so it's easier to make a decision for. You might be like, oh, well, why isn't there a major highway connecting Miami with Boston? Like directly, right? But then you're like, oh, because there's like 8 cities between them and they can just go to each city. So it's just a tool, right? It's a tool to make things easier to digest. Sometimes things are crowded. Sometimes things are not easy to look at. This is easier to look at, okay? For example, we're going to be doing 3 different problems right now where a graph can be used to simplify a diagram or a map, okay? So this first example is a map. We're going to represent the diagram as a graph. We're going to make sure to label our vertices. Now, when you're making a graph, you want to make sure you understand what your vertices are and what your edges represent, okay? Now, in this case, it would make sense for edges to represent what? Bridges, yeah. Yeah, it's a very common use, yeah? And then our land masses will be vertices then, right? So essentially what we're going to do is we're going to draw our vertices. So we have landmass A, B, C, and D. And you don't have to draw them in a diamond shape. You can draw them in however way you want, okay? 2 graphs are considered equal if you have the same edges connecting the same vertices, okay? They don't have to look the same. They just have to have the same edges connecting the same vertices, which means the math is the same, right? And then we're just going to draw. We're just going to connect our dots. So you see we have a bridge right here. We're going to connect A to B. But you see this bridge? That also connects A to B, right? Do you think we have to represent that? Yes. Yes, we do. you want to make sure you're representing both ways to get from A to B, because that's potentially a different solution if you consider two different ways to get from a place to another place. So we draw every single bridge. B to D has two bridges. There's a bridge from B to C. There's a bridge from A to C. There's a bridge from D to C. So this graph represents that map. And this could be easier to work with if you're doing like some kind of project or figuring out like something, right? Pictures are almost never easier to work with than like something simple like this. This you can manipulate. In fact, you guys ever, you know GeoGebra? If you had me, you probably used that in geometry. GeoGebra is like, it's like a geometry tool. You just like, you can make squares and stuff in it, diagrams, all that. Well, you can make stuff like this in GeoGebra too. And then what you can do is you can take a point and drag it without having to like redraw anything. You can just move it. That's going to be like a program that would make something like this super easy to work with. You know what I mean? Versus a picture a picture is just a picture. It's static. It doesn't ever change. I mean, you can change how big or small it is, but like I couldn't take this landmass and go over here with it to make it easier to look at. But you could with this. Next. Here's a map of the southwestern United States. California, Nevada, Utah, Arizona, Colorado, New Mexico. We're going to represent the diagram as a graph. Now this one, it might be easier to start with. What are the vertices going to be? States. So let's go ahead and do that. Let's say we got California, we have Nevada, we have Arizonas, we got Utah, we got New Mexico, we got Colorado. Wake up! Your alarm's going off. Why am I a jerk? I don't know. So if the vertices are the states, then what are the edges going to represent in this problem? Like, what am I going to connect California to? Say what? Yeah, the state's borders. We're going to connect two states that share a border, okay? So if you can physically walk from one to the other, we're going to connect them. There's only one condition, and this is like a kind of a fringe condition, but it pops up more than you'd think it does. We're going to make sure that they're connected by an edge and not just by one point, right? So like we're not going to consider New Mexico and Utah connected. They share a point right here, but realistically, if you were to drag your foot over that point, because a point by definition has no dimensions, you would be stepping into Colorado, Arizona, and Utah all at the same time if you tried to go from New Mexico to Utah, right? So it's ambiguous. It's like you wouldn't really be able to go directly from here to here. Like you would in one or two steps, right? But not like in an instant. So that's a tricky one. So rule, if they're connected by a corner, it doesn't count. Okay, it has to be connected by an edge. I'm saying that because it pops up more than you think it does. It can be a really small edge, and that's fine. It's just got to be an edge. So California is going to be connected to Nevada and Arizona. They share a border. Arizona is connected to California, Nevada, Utah, and New Mexico. Nevada is connected to Utah, California, and Arizona. Utah is connected to California, or not California, Colorado, Nevada, and Arizona. Colorado is connected to Utah and New Mexico. And there we go. There's our complete graph. Now, again, if you were doing something where you wanted to know, it's going to, everything I say is going to sound like a math problem here, right? But there are real world applications to it. But if you wanted to figure out if you could go to each one of these states without entering the same one twice, it'd be easier to work with this than this, okay? Now let's look at the degrees here, just for funsies. What's the degree of California? Faith? You got your thinking face on. How many edges are connected to it? 2. So the degree is 2. What's the degree of Nevada? 3. Very good. How about Arizona? 4. How about Utah? 3. Colorado? 2. New Mexico? 2. Good. Believe it or not, the degrees they come into play way more than you'd think. They're actually super important. Okay? You'll see that tomorrow. Next. Here we got a gym. We want to draw this, like, what's it called? Floor plan as a graph. Okay? So if we were to draw this as a graph, what would our vertices be? The rooms. That's exactly right. So the vertices is going to be our rooms, including outside. So we're going to say outside. We have Ray's training room. We have locker room A. We have Sierra's training room. We have the health and weight room. Keegan's training room. Locker room B. And Chet's training room. And again, it doesn't have to look like this. You could put all these in a circle if you want to. I don't care. It's up to you. Okay. Now, if rooms are the vertices, what are the edges? The walls? That wouldn't make much sense, right? Because if, like, for example, if I connect locker room A, it shares a wall with the health and weight room. But is there any physical way to get from A to the health and weight room? No. Doors are going to be the edges because there's a physical way to go. Now, am I saying you couldn't use walls here? You could use walls, right? And connect locker room A to health and weight room. The problem is, what are you going to use that for, right? There's probably a lot more applications if you can physically get to one room versus if you can't. You know what I'm saying? So we are going to do rooms as vertices, doorways as edges. Let's start with the health and weight room because that one has a lot of doorways, right? The health and weight room has a door to Ray's training room, Sierra's training room, Keegan's training room, and Chet's training room. But it also has 2 more doors. On the left, we can go outside. On the right, we can go outside. Do we have to count both those doorways? Yeah. Yes, we do. And, you know, outside's all the way up here, right? So this is going to look kind of funky, but we got to connect them. We're just connecting the health and weight locker room to outside, okay? But outside's just 1 point, so they all have to go to the same point. This is where it might be useful for you to rearrange the vertices once you see this, right? If you're not sure of what you're looking at. Okay, now let's go down. We go to Keegan's, it's connected to locker room B. Locker room B is connected to the Chet. And then we got the same kind of shape up top. Except locker room A also goes outside. So we connect it. So this graph represents this, okay? Now again, I could put all these in a circle if I wanted to and do the same connections, and it's considered equivalent. So when I grade this stuff that you guys do, I don't look at what it looks like. I look at what are the connections, okay? Because the connections are what's important here, not how it looks. Okay? Everyone clear on that? So there's like literally an infinite number of ways you can do this. But there's only one way you can connect everything. in this way, I guess. Okay, keep it rolling. Some more vocabulary. Now this is the part 2, so this would be on the next page. This first 2 homework assignments are so quick, guys. Like, I part of me feels bad for giving you 2 pages, but at the same time, I really don't because it's so easy. You know what I'm saying? Well, whatever. Okay, so most of the time when we talk about graphs, we're going to be talking about traveling from a vertex to another vertex. And you might have seen that with all the examples we had where like the bridges were edges, where the borders were edges and the vertices were states, where the doorways were edges, not the walls. Right, Braden? So most of the time we're traveling. We're going to be talking about going from one point to another point. Now, when we go from one point to another point, we call that a path. Okay? So what's the path of going from A to D? So paths are sequences of adjacent vertices and the edges connecting them. Usually when you do a path, you'll just list the vertices you're going in the order that you're going in. For example, you'll do like A, B, C, D. That means you're going from A to B to C to D, okay? Like you don't have to use arrows. You don't have to make it hard on yourself. You literally just will put the letters in the order that you're going in. Now we do have a special kind of paths called circuits. And if you've ever played Mario Kart, you know what a circuit is, okay? Or if you ever knew anything about electricity. A circuit is just a path that ends where it started, okay? Like Mario Kart. The finish line is usually where you started. So a circuit could be just like that path we just had, but then when we're done, we end at A. A circuit will always end at the same point it started. A path doesn't have to. All circuits are paths, but not all paths are circuits. Okay, this is like the square rectangle thing. Any questions? Okay, so I got this little house. It's a graph that looks like a house. Yeah. What I want to do is just talk with you guys, and we're going to give 3 examples of, well, maybe not, maybe 3, maybe not 3. 3 examples of what's a path, what's a circuit, and what's not a path, okay? So we'll do path first. Can someone give me an example of a path you could take on this graph? Shabad? A, B, D, E, C. I love it. So visually, that path would look like this. But wait, we didn't cover every edge. Is that okay? Absolutely, that's okay. You do not need to cover every edge. What about this path? Does that work? But we didn't cover every vertex. Is that okay? Yeah, that's okay. Just because Starbucks and Target are in Lafayette doesn't mean we have to go, right? We just want to.
These are your just printing stuff for decamp when this came out.
Thank you. See, Lizzie, that's how you student aid. Thanks, Jesus. I miss you. That was weird, right? It's okay. I forgot to. I would have told you. Yeah, you do not need to hit every vertex. You do not need to hit every edge for it to be a path. There are special paths where you do hit every vertex. There are special paths where you do hit every edge. They do not exist in every graph. Okay, have you guys ever played the pencil game, like trace everything without lifting your pencil up? That's what we're going to be doing. That's like actual math, believe it or not. But they don't exist in every graph, okay? So these two are perfectly good examples of paths. Now let's talk about circuits. Someone give me an example of a circuit. Andrea.
A, B, C, D, E, C, A.
Well, one more time. A, B, C.
A, B, C, D, E, C,
Now, there's one issue with that one. And in fact, let's go ahead and talk about that now. I'm glad we brought it up. There is one condition for stuff to be paths. Who can see it? Tommy. I can't get from C to D in one go, right?
I think you misheard me.
Did I mishear you?
A, B, C, D, E, C, A.
Oh, A, B, C, E. Okay, sorry, Andrea. Well, either way, we've still brought it up, which is still good. We were going to do that anyways, right? Yeah, A, B, C, D, E is not a path. And why is this not a path? You cannot directly go from C to D. This is the one condition. There has to be an edge between any adjacent vertices for you to make that move. Okay? You can't just drive through cornfields. You could, I guess, but you're not supposed to. Okay, so going back to Andrea. Sorry, Andrea. You said A, B, C, E, D. E, not D. And then where'd you go from there? B, A?
A, B, D, E, C, A. Yeah, back to A.
Okay. This is a good one. Are you allowed to hit the same vertex twice? Absolutely. You're absolutely allowed to hit the same vertex twice. There's no rule against that. Like I'm talking paths and circuits, there's one rule, and it's just that you have to connect them with an edge, right? Again, there are special circuits and paths where you can't travel the same vertex twice, but there's no one saying that you can't go to Starbucks twice in one trip, right? Am I clicking with all the basics in here? I'm clicking with Lizzie. Any questions? Do y'all feel like you know what paths and circuits are? Okay. Now, a couple more words. I know these are easy words to understand, though. We have connected, we have disconnected, and then we have something called a bridge, which is going to come up later. Connected and disconnected are really easy to understand. We consider a graph connected if between any two vertices, so if you start from anywhere and end on anywhere, you can do that move, okay? For example, the last graph we had was connected because if I went from A, if I started at A, I could go to any other vertex. If I started from B, I could go to any other vertex. If I started from C, I could go to any other vertex. You get what I'm saying? Like in a path. They don't have to be connected. They just have, or I guess they don't have to be adjacent. I just can get there if I needed to. We would consider those connected. Now, if there's any vertex on your graph where you can't get to another vertex or any other vertex, so for example, if I was at A and it was impossible for me to make a path to get to F, then we consider that disconnected. There is a weird thing with that too. So let me show you an example. Here's a graph that is connected. Okay? If I add, let's add 3 points. If you consider these graphs together as one graph, they would be disconnected because it's impossible for me to get from here to here and vice versa. Okay? So that's like the main thing. I mean, it's really easy to tell if it's connected or disconnected when it's in this format. But there is one tricky part of it, okay? Let's say instead of drawing the triangle over here, I draw it inside this rectangle. Now, is this connected or disconnected? This is still disconnected. I know it looks connected, but again, this isn't like geometry, okay? When you're at a point, you have to travel to another point, right? So this edge, it only goes here and here. It doesn't actually stop here. You can't just stop in the middle of an edge, okay? You're either going this way or this way at the start. So you can only stop when there are vertices, all right? Now, this is disconnected, but if I do something like this, now it's connected, okay? Because now I can go from here to here, and from here I can either continue onto the triangle or I can go onto the square, all right? That's where it can get a little confusing, but it do be like that though. And then the last thing we're going to talk about is something called a bridge. Now, a bridge is an edge that when it's connected, or when it's removed, excuse me, it would cause the graph to be disconnected, right? So if I drew that triangle over here again, first of all, if I just look at the square, none of these are bridges, right? If I remove this bottom, I could still get from this point to this point by going all the way around. You guys get that? So any closed shape, like theorem time, any closed shape doesn't have any bridges, all right? But if I went like this would be considered a bridge. Oops. Because now if I remove this shape, it would be impossible to get to any point on the square to any point on the triangle. So you gotta use your imagination when it comes to bridges. You have to imagine yourself taking that and making it not exist. So sometimes it's easy to redraw it and just erase it and see what happens, right? Now, it's important to understand that when you determine what a bridge is, you can only remove one edge at a time, right? So you remove the one edge, determine it's a bridge. If it's not a bridge, put it back, remove a different edge. You can't say, well, this would be a bridge if I remove this edge and this edge. You can't do that, okay? It's just removing the one edge. If you have to remove two edges to make it a bridge, guess what? It's not a bridge, okay? For example, let's represent this as a graph. We'll do it the same way we did the American Southwest. We'll do the American Southeast. Pretty easy to make this graph, huh? Now the question is, which edges are bridges? Let's start with the far left here. Texas to Louisiana. Is this a bridge? It is a bridge. Because if I remove this border, and this was the only thing that existed, everything else is water or void, right? If I remove this edge, it would be impossible to get from Texas to anywhere else, right? So that's a bridge. How about Louisiana to Mississippi? Is that a bridge? Yes. Because again, you're isolating Texas, you're isolating Louisiana also in that case. How about Mississippi to Alabama? Is this a bridge? Absolutely. If I remove that, then you'd be isolating Texas, Louisiana, and Mississippi from the rest. Now we get to this. Is anything in here a bridge? No. And again, we can go back to any closed shape would not be a bridge, okay? And that's because I could remove, for example, let's say I remove, let's get another obvious bridge out of the way, actually. Georgia, South Carolina is a big old bridge for the same reasons the other ones are. But if I remove any of these edges here, Alabama, Georgia, Florida, Georgia, Florida, Georgia. For example, let's do this one. I removed it, but we can still see it's all connected, right? So that's not a bridge. Let's do Georgia, Florida. I removed it, but we can still see it's all connected, yeah? And then finally, Alabama, Georgia, remove it, still connected. So anytime, it's not just a closed shape by itself, anytime there's a closed shape inside of a graph, none of those are going to be bridges because there's always going to be a way just to go around, okay? So the only bridges are the single edges. Any questions? I think that's it. That's 2 lessons in one day, y'all. It's a lot of vocab, though. I do understand that. It do be a lot of vocab, though. And we went right up to the end of the day, huh? As far as homework due dates go,